Hello, and welcome. Today, we're going to take a closer, more detailed look at one of the most fundamental and accurate instruments for measuring electricity, the Permanent Magnet Moving Coil, or PMMC, instrument. You've probably seen meters like this on old radios or in a science lab. Let's break down exactly how this clever device works, piece by piece, in simple terms. At its very core, the PMMC instrument operates on a basic principle of physics. When you pass an electric current through a wire that is placed inside a magnetic field, the wire experiences a force that makes it want to move. The entire instrument is designed around this single idea. Let's start with the foundation of the device, the permanent magnet. You can see it here as the large structure with a north and south pole. Think of this as the stage on which the main action happens. Its job is to create a powerful and, most importantly, a constant and unchanging magnetic field in the space between its poles. This field is the invisible force that will act upon our coil. Now, sitting right in the middle of this magnetic field is the cylindrical core. This is typically made of soft iron. It's not just a simple spacer, it plays two critical roles. First, it concentrates the magnetic field lines, making the field much stronger. Second, it shapes the field into a radial field. Imagine the spokes of a bicycle will all pointing towards the center, that's a radial field. This special shape is crucial because it ensures that no matter how much the coil rotates, the magnetic field is always cutting it at a perfect right angle. This results in a uniform turning force, which in turn gives us a linear, evenly spaced scale, making it very easy to read. Now for the star of the show, the moving coil. This is a very fine, delicate copper wire that is carefully wound many times around a lightweight rectangular frame called a former. The former, usually made of aluminum, simply provides shape and support for the coil. This entire assembly, the coil on its former, is where the electric current you want to measure actually flows. This coil assembly is mounted on a spindle, allowing it to rotate freely. But how can it rotate with almost no resistance? That's thanks to the pivot and jewel bearing. Think of this like the axle of a high-performance spinning top. The spindle has a tiny, sharp, hardened steel point at each end, which is the pivot. This point rests inside a tiny, cup-shaped jewel, often made of a super hard and smooth material like sapphire. This combination creates an incredibly low friction point of rotation, making the instrument extremely sensitive and able to respond to even very small currents. When current flows through the coil, the interaction with the magnet's field creates a turning force, or torque. This causes the entire assembly, including the spindle, to rotate. Attached to this rotating system is the long, thin pointer. As the coil turns, the pointer sweeps across the calibrated scale, which is marked with numbers representing the value of the current or voltage being measured. But what stops the pointer from just spinning wildly? And what brings it back to zero when the current is turned off? That's the vital job of the two spiral springs, one at the top and one at the bottom. These springs do two things. First, they provide the controlling or restoring torque. The more the coil tries to turn due to the current, the more the springs wind up and push back in the opposite direction. The pointer comes to a steady rest at the exact position where the turning force from the current is perfectly balanced by the restoring force from the springs. Second, the springs also act as the electrical pathway, carrying the current to and from the moving coil. For ultimate precision, a couple more clever features are included. You'll notice small balancing weights on the pointer arm. These are like the weights a mechanic uses to balance a car tire. They ensure the entire moving system is perfectly balanced, so that gravity doesn't affect the reading, regardless of whether the meter is lying flat or mounted vertically on a panel. Finally, look closely at the scale. You'll often see a thin mirror strip running along the arc of the scale markings. This is a brilliant little feature to eliminate what's called parallax error. This error happens when you look at a pointer from an angle, making it seem like it's pointing to a different value. To get a perfectly accurate reading, you simply move your head until the pointer completely covers its own reflection in the mirror. At that moment, you know your eye is looking at it from a perfect 90-degree angle, and the reading you see is the true one. So, in summary, current enters the springs, flows through the coil, which then experiences a force in the permanent magnet's field, causing it to rotate on its jewel bearings. This rotation, which is precisely opposed by the springs, moves the pointer across the scale, giving you an accurate measurement of the current. It's a beautiful symphony of simple physical principles working together to create a reliable and precise instrument.